Welcome everybody. My name is Summer Ash and I'm the STEAM Education Manager here at the VLA in Socorro, New Mexico. I'd like to bring my team on, so Faith and Montana and Tyler, if you can turn your cameras on as well. So introduce us all. So this is the STEAM Education team for NRAO. Faith, you want to introduce yourself and your job?
Sure. Hi, everyone. I'm Faith Vowler. I'm the education specialist here at NRAO, also in Socorro, New Mexico.
And Montana?
Hi, everyone. I'm Montana Williams. I'm also in Socorro, New Mexico, and I'm a tour guide and a PhD student.
And Tyler?
Hello, my name is Tyler. I am also a PhD student in Socorro, New Mexico, and a VLA tour guide.
Awesome. So I'm going to hand it off to my colleague Faith right now to get the tour started. And I will join back in when we get to introduce a lot of our exciting guest speakers today from the Central Development Laboratory. So take it away, Faith, and we'll.
Thanks, Summer. All right, so hello everyone, and thank you so much for coming to our tour today. We also just want to give you a heads up that the internet in New Mexico here is not always the best, so please bear with us if we have any technical difficulties. So just some quick housekeeping to start off here. If you have questions for us, please use the Zoom Q&A feature, which you can find right down here on your screens. And so we're going to have a dedicated time to answer your questions later on during the tour. And some of them we might be answering right in the Q&A feature. So make sure to check back and look at that again to see if your question's been answered. And then others will be answering out loud. And you can use the chat feature to talk to your fellow attendees. We will be putting occasional information in the chat for you as well. And if there's any technical difficulties that you want to let us know about, again, you can use the chat feature. And please make sure that your chats are set to talk to all panelists and attendees. And all of the website links that we put in the chat during the tour, we're also going to send a follow-up email after the tour, and that'll have all those links as well. So if you don't get the chance to click on them or see them during the tour, don't worry, you will still get them. And we try to answer as many questions as we can, but we don't always have time for all of them. And so if we're not able to answer your question, then during the tour, you can also go to our website and use our Ask an Astronomer feature. You can search the archives to see if your question has already been asked. And then if it hasn't, you can submit your own. And usually the answers there are posted online within a few days. And we're also going to have 4 different guest speakers who will tell you about the work that they do at CDL during this tour. So we'll have Matt Morgan, who's a scientist and research engineer, Denisse Almeida, a mechanical engineer, Jennifer Jackson, a technical specialist, and Bert Hawkins, who's the assistant director. So before we get into CDL itself, just to give you a bit of background about who we are, the National Radio Astronomy Observatory. So we were founded in the 50s with the goal of designing and building and operating and maintaining state-of-the-art radio telescopes to study the radio light that comes to us from space. And we have 3 major radio observatories that we're responsible for. There's the Very Large Array, or VLA, here in the United States in New Mexico. We have the Very Long Baseline Array, or VLBA, which is across North America. And we have the Atacama Large Millimeter Submillimeter Array, or ALMA, which is down in Chile in South America. And NRAO is funded by the National Science Foundation. So since we are government funded, that means a small portion of your tax money does go towards paying for the work that we do. So that's why we think it's very important to be able to share our work with you and have these kinds of events. So the Central Development Laboratory is located in Charlottesville, Virginia, which is also where our the headquarters of NRAO are, and it's on the campus of the University of Virginia. And as you can see in this top picture here, it's in a very lovely building called the NRAO Technology Center, or NTC. And you might have seen photos of our radio telescopes and pictures, scientific images that we've made with them. And there's a lot of technology and expertise that we need to bridge the gap between the data that those telescopes get and the pictures. And so that is where CDL's work is really important. And they work with astronomers and engineers to address needs of the telescopes and our technology as they arise. And so as you can see, the mission of CDL is to support the evolution of our NRAO's existing facilities, and as well as the expertise to build the next generation of radio telescopes and instruments. And so they have multiple patents, and it played a very large role, critical contributions to ALMA and the Event Horizon telescope, which was made up of multiple different observatories and institutions around the world. And so CDL makes sure that our telescopes are always evolving and improving. So now I'm going to stop sharing my screen, and Summer's going to just share a brief video with you that provides a more good introduction to CDL.
Thank you, Faith. Let me pull up this video. Okay, this is a bit of a teaser trailer for what goes on at CDL.
CDL really is what makes the magic happen.
The Central Development Lab is our engineering division for NRAO.
People come from all over the world to get us to design receivers for their applications. So we develop the receiver, the mixers, the low noise amplifiers, the best in class type of components.
Those engineers that are developing those technologies work closely with our scientists in order to tune the technologies that they develop to solve science problems.
Without the sensitive receivers and the instrumentation that they have invented here, we wouldn't be able to untangle all of those great messages that are in the radio waves. So the dish just catches it and brings it to a focus, and then it comes down into the guts of the telescope, which all happens here at CDL.
The Central Development Lab at NRAO is excellent for radio astronomy instrumentation, as it combines all of the different disciplines in one house, and you're right next to all of the astronomers.
There's all sorts of trades that are supporting the actual operation of any given observatory. There's very few astronomers who work here, maybe 20% astronomers. It takes railroad engineers, it takes computer engineers, it takes, mechanical engineers, carpenters, welders. We are revealing mysteries of the universe. We're understanding our place in the universe better. The advances that make those discoveries possible benefit everybody.
Okay, hope you enjoyed that. There were a couple cameos in there of our upcoming guest speakers. Right now, I would like to introduce our first speaker. So Matt, if you could turn on your camera and your microphone and join me.
Thank you, Sam.
Thanks. Matt is a research engineer at CDL, specializing in microwave and millimeter wave integrated circuit and systems design. And we'll find out more about what that means. He's the head of the Integrated Receiver Development Group and inventor of reflectionless filters, a novel concept in filter design that has found widespread use in scientific, commercial, and military applications. He has over 17 patents. As Faith alluded to earlier, a lot of patents come out of CDL. And he's authored 3 books about E&M theory and microwave electronic circuit design. Matt, you're very accomplished.
Thank you very much.
How did you first get interested in science and engineering?
I've always been interested in science and engineering since I was a kid. I was raised on Star Trek, you know, and so I always wanted to participate in exploring the universe. And I was particularly drawn to how stuff works, you know, and so I think that's what got me into engineering. So it's a pleasure for me now to be able to practice engineering in a way that has such a rewarding application. Yeah.
And how did you come to NRAO and CDL? Did you come straight to CDL?
I did out of graduate school. There's a sort of an interesting story there I've told before. I was studying electrical engineering in college and was particularly interested in microwave and millimeter wave electronics, which is the kind of technology you use for wireless networks and cellular cell phone handsets and that kind of thing. And that's kind of what I thought I would do professionally. But when I was applying for graduate school, this was in the summer of around 1997, I think it was, when the Hale-Bopp comet was coming through. And I got fascinated by that. I got some of the magazines and I started working, I started as a hobby doing some astrophotography in my backyard. I got a cheap telescope with a little DC motor and a cheap camera that I could use to track and take some pictures. I still have the photos in my closet where nobody can see them because they're not very good, but nonetheless, it was an interesting hobby for me. And then I was applying for grad school a year or two later, and I had to write essays about what I did. And I ended up writing about that as a hobby. I didn't actually think it would have anything to do with my career, but I thought it would make me seem well-rounded. So I wrote about astrophotography, but it actually kind of became the linkage between electrical engineering and astronomy, which were sort of my dual interests. And that was noticed by Sandy Weinreb, who was working at the Jet Propulsion Lab in California at the time, and he was reviewing applications for grad school at Caltech. He ultimately ended up being my advisor there, and really he's the one who pulled me into radio astronomy as a career. So I sort of jokingly tell people, tongue in cheek, that I don't believe in astrology, but the passage of a comet really did have a big impact on the direction of my life.
I love it.
Yeah.
So as we sort of phrase, CDL is what makes the magic happen. And in that video, there was a lot of mentioning of the guts of the telescope. So I was wondering if you could elaborate on what that actually means, because when we normally give our VLA tours, we talk about the dish and we talk about the receivers and detectors, but we don't really go much farther than that. So what are the guts? What are the rest of what else is the rest of the inside of the telescope doing?
Sure. Well, it varies a bit depending on the actual telescope, what its frequency range is, and what its target science application are. But a typical system will go something like this. Obviously, the part that everybody sees, the big parabolic dish, and that's really just a collector, because collecting area is one of the first things that we need in order to receive the weakest signals from the farthest reaches of the universe. And so the parabolic dish, that's really just a concentrator that focuses the wave from the sky onto a device we call a feed horn. And that feed horn is just a type of antenna that couples your wavefront into an electronic circuit. From there, we have what's called an orthomode transducer, which is a device that separates polarizations. So people who have polarized sunglasses, for example, would know that light is polarized in different ways. We separate the two polarizations from the sky onto separate channels to be processed independently as separate signals. Then typically we'll have a cryogenic amplifier to amplify the signal to make it stronger, because again, the signals we're looking for are very weak, and we want to make sure we amplify and increase its amplitude, that's what an amplifier does, as quickly as possible before we pass it into any other electronic components that might add noise to it. So usually the feed, the ortho-mode transducer, and the amplifier will be cryogenically cooled to reduce their noise contribution to the minimum amount possible. From there, we go into our room temperature analog electronics, where we'll have more amplification typically. We'll have some gain adjustment because we're looking at cold sky, we're looking at a strong source, we might even be looking at the sun, and so our power level will change. Then we'll usually have a mixer to down convert the signal usually from a higher frequency down to a lower frequency where it can be digitized more effectively. We'll have filters at various places throughout the signal path to select a certain frequency band that we want to look at a particular time. And then eventually we'll get to an analog to digital converter or digitizer, which changes our signal into bits. And then we'll have a laser transmitter to send those bits out over an optical fiber to a back-end signal processing facility where we have essentially a supercomputer to collect data from all the various telescopes and combine them to form images. So that's sort of front to back what we do.
And the cryogenics that you mentioned, you also alluded to needing to remove or keep extra noise from coming into the signal. But in this case, noise is not what people often think about as sound noise. What kind of noise are you talking about, and how is the cryogenics helping?
Sure. What we're really talking about is random electronic interference. So if anybody remembers the old analog television sets, if you get the white snow on the screen, or if you tune to a station in your car where there's no radio station, you'll hear the static. That's what we call electronic noise. And what it is, if you think about a radio telescope, what it's doing, it's detecting an electromagnetic wave, which is light, which is really just forces acting on charges like electrons in our system. So we're looking for those electrons to jostle slightly because of the passage of an electronic wave. But the thing is, those electrons are already jostling a lot because of thermal excitation, because they're just buzzing around at random. And that's what causes that static that you'd hear on your radio or the snow on your television screen. So to make the most sensitive system possible, we want to slow those charges down to make them as still as they possibly can before we try to detect the wave, so we can see the smallest amount of movement. So that's sort of
how cold are we talking?
So it depends on the receiver. For most of our receivers in sort of the microwave or millimeter wave range, which is sort of hundreds of megahertz to a few gigahertz to a few hundred gigahertz, to about 100 gigahertz, we'll usually use a cryogenic amplifier cooled to about 20 Kelvin, which is about minus 270 degrees Celsius.
Yeah.
For higher frequencies than 100 gigahertz, we'll use a superconducting mixer technology, and they have to be cooled to about 4 Kelvin. So we'll have another refrigeration stage after that. And we're doing some new interesting research now on some new devices called a traveling wave kinetic inductance parametric amplifier that has to be cooled to 10 or 12 millikelvin in order to work. And so we get to very cold temperatures.
Wow.
That's Kelvin. So 0 Kelvin would what we call absolute zero,
right.
Minus 293 Celsius.
Right. Your 4 Kelvin remark made me recall that I think our news group did a feature on CDL because the 4-degree Kelvin chamber, or the cryogenics, wherever you're running that, is technically the coldest place in Virginia.
Yeah, it probably is.
And probably much of the surrounding area, but
except
definitely.
when we're running our 10 millikelvin doer, in which case that becomes the coldest place.
Yeah. Which maybe we didn't know about at the time that was coming online. Yeah. Is there such a thing as like a typical day at work for you? Or what kind of things do you find yourself getting into on a day-to-day basis?
Well, I wear a lot of hats, actually. I work on many different projects. So I have, I work sometimes in support for existing telescopes, like out in New Mexico or in Green Bank. Most of the time I'm working on development of new electronics for new telescope systems, either for a dedicated telescope, like we have the next generation very large array, which I think you've done some tours for that as well.
Correct, just last month.
Yeah, so I'm involved in developing the electronics plan for that. And so unfortunately that involves a lot of documentation and meetings, but sometimes I actually get to sit down and do hardware design, which is more fun for me. And then I always have on the side some just forward-thinking research projects that I'm doing to think about, well, here's a problem, we typically build receivers this way, how could we do them better? And I like to try and keep some creative ideas in progress at all times. So.
Great. So I'm going to thank you for your brief time right now, Matt, but we'll bring you back for the Q&A at the end. And I would like to bring on our next guest, Denisse. Can you turn your camera on and join us? join
Hello.
me. Hi, how are you?
Good. How are you guys doing?
Doing good. So Denisse, let me introduce her for a second. Denisse is a mechanical engineer who's passionate about astronomy and anything having to do with space, right there with you. And she enjoys working at NRAO's CDL because she can use her mechanical engineering background while working in the astronomy field. And it also allows her to do hands-on work. And so I think, Denisse, you actually have some slides that you'd like to share that really illustrate a lot of that hands-on work that you get to do.
I do, because I'd actually like to show it, because I think what we work on is some pretty cool stuff. If I can figure out my screens here, give me just a second. So
That works. It's working.
Awesome. Perfect. So yeah, so I just wanted to show a little bit of slides and have some sort of I guess, route as to where I'm going. So as you mentioned, I'm a mechanical engineer, and in my day-to-day, I end up using CAD to design, create, and update models of components that are going to be used on radio telescopes. And I also help different teams at CDL design the ideas that they have in mind, which is something that I really like, collaborating and working with scientists and engineers. It's very cool to be able to bring those things to life. Aside from being a mechanical engineer, I'm also a plater. So part of my job is to plate parts that are created on site to gold, which is, I think that's really cool. And that's a hands-on work that I like a lot. And besides plating the parts that we make on site, we also plate outside work as well. So a couple of examples of the CAD models that we create here at CDL. This is the Band 6 cartridge for ALMA. ALMA is a radio telescope in Chile. And the Band 6 cartridge is basically a receiver, and ALMA it captures signals from 10 different frequency bands, sorry, and this is just one of those cartridges from the 10. And as you can see, this cartridge is very complex, has a lot of parts. And the funny thing is that I started here a year ago when we were technically working from home because, COVID and the whole situation. So in my mind, coming here, I had a bigger concept of these things, and I thought this cartridge was something big. And when I saw it in person, it's something so small and incredibly complex and detailed with so many parts. And that's most of the stuff we do here. It's very tiny things, and it's very cool.
I was just going to ask you, what sort of scale is this cartridge on?
I'm not very good at depicting scales.
Oh, that's okay.
But I'll just do probably like about that tall. It's not very big. It's heavy.
Where's your bottom hand?
There.
Yeah. Okay. So maybe 2 feet.
Yeah. It's not very big, but it is dense. But it is very cool when you see all these parts in person. And then another part that I'd like to illustrate that we're very known for are the low noise amplifiers, something that CDL is known for pretty much around the world. As you can tell on the bottom slide, these parts are minuscule, they're tiny, but they are so complex and filled with so many features. And it's just basically an example of the part and the drawing. And then moving on, and I just want to talk about our machine shop and how we have an on-site machine shop that creates a bunch of parts and components that we send basically to all these radio telescopes. And the precision in this machine shop is so high. It's basically it's the tolerances that I have here on the slides, but since it's not very easy to have this as a concept in your mind, well, the average human hair has a thickness of 80 microns. This machine shop can go down to 5 microns, and it's pretty cool. And Matt earlier was talking about an OMT, an orthomode transducer, and that is here on the side, and I took a picture of it next to a little paper clip so you can see just how tiny that part is and the complex little features that it has inside.
Mm-hmm.
But no, and then the other part of my job is doing plating. So we have a plating and chemistry lab, and we do gold plating. Here on the left, we have some K connector adapters, which if you don't mind, I'll go back. You see it all kind of relates to each other, which is cool. We have the K connector adapters, which go on the low noise amplifiers, and those there are plated. On the left, you see it in gold. On the right, it's brass. And with brass, it's kind of hard to tell when it turns into gold, but it's more apparent with the parts on the right, which were actually outside parts. But it's really cool because even as I'm working on this on site, I just dip it and it turns into gold, and it's like magic right before your eyes. It's really cool. I think it's
And
cool.
can you talk about why gold or why these particular metals?
Yeah, so the reason that we do gold is because gold provides a corrosion resistant layer on these parts, and it also provides good thermal conductivity for both heat dissipation and cooling and cryogenic applications. But that's pretty much what we do it. And most of our parts come from brass or copper, and plating them into gold. It's not a tedious process, but if you're going from something like, say, aluminum or stainless steel, the process becomes a little bit more complex because you have to do a couple of more steps in there. And it's very interesting because coming from a mechanical engineering background, I did not really think I'd be doing chemistry. So I feel like a little chemist. It's awesome. And then the other thing we do in the plating lab is electroforming, where we grow a metal object from scratch rather than plating an existing part. So if you look here on the picture on the top right, that aluminum part on the left is what comes out of the machine shop. And then we gold plate that, and then we grow copper on it. So growing copper is that you dunk it into a copper tank, you're growing copper on it. And then eventually what you have left is that you're gonna put that final part. So I don't know if you guys can see my mouse, but here we're growing copper. So the reason that we do this is because, let me see if I can try to explain this, because it's kind of a hard concept to explain because I even took a while to understand it. But these features that you see here on the outside, you essentially want on the inside. So this is a mandrel. So because it's so when you look at this part on the inside, and I'm sorry I couldn't take a picture from the inside, you're going to see kind of like a ribbed part going on the inside. And if you try to machine that, that's a little bit difficult to do. So what what my manager here at the plating lab decided to do or thought of was electroforming, which is an incredibly clever concept where you create a mandrel and then you create the features that you want on the inside. You grow copper on the outside, and then you send this back to the machine shop. They solder the flanges here on the end, and then they send that back to us. And then we use some sort of acid solution to kind of dissolve the mandrel so this inside is on the inside, we dissolve it and we create this final part with these internal features on the inside. That process takes a couple of weeks to do. Now that we're working from home a little bit, it takes probably about a month to complete just one of those parts. And but it's a very cool process and it takes a while, and you kind of want to make sure you get it right on the first try, because then the machine shop has to do the part all over again. But
it seems like a very chemically advanced version of casting, or the way sculptors and artists would kind of do these kind of things.
Yeah, but yeah, and then it is true. And then so this is kind of the best example I could find. This is an example of what we have in the lab here that I'm working with currently, and this is the finished product, which actually this comes out, it's kind of a variation of what comes out of this, and it's a very hard concept to grasp, but it's pretty cool. But those are the end of my slides. If you want to read more about CDL, feel free to check us out at our page, and I'm gonna go ahead and stop sharing because that is it for me as far as slides go.
No, that was amazing. Thank you. And just a reminder to the audience that we will be sharing all the links that we mentioned in this talk with the follow-up Zoom email. So Denisse, before I let you go, what drew you into engineering in the first place?
So since the 5th grade, so in the 5th grade, I remember that I saw an earth science book on astronomy. I was really bored by everything in that earth science book. And unfortunately, they didn't teach astronomy, but that's the thing that I was captivated by, and rockets and satellites and everything that went to space. And I think from that time on, I decided, I think I'm going to become an aerospace engineer, not knowing at that age what that entailed, or mechanical engineer. But I went through with it, and astronomy has always been a passion of mine. Space, as you mentioned earlier, and as you can probably see by my background. But I mostly got into engineering just because I like the whole aspect of putting things together, finding out more about them. I used to take like little speakers that broke for your iPod and deconstruct them and see what was inside of them. Machine shops, I love them. I mean, they probably won't let me near our machine shop, but I love it. But it's something that I've always been driven to because I just like seeing how things work, and I like making them work, and it's great. And just the fact that I can apply it to astronomy is astounding, especially here. at an NRAO, which is like a national lab. It's so cool.
Well, we're excited to have you.
Awesome.
Okay, I'm going to bring our final guest speaker on, Jennifer Jackson. So thank you, Denise, and we'll see you back at the Q&A. And Jennifer.
Hi.
Hello. So Jennifer Jackson is a technical specialist with the Band 6 cartridge and mixers group. Band 6 being something that you just saw a slight hint of in Denise's presentation. And Jennifer is also an Air Force veteran, and she was inspired by the telescopes at the VLA while she was stationed for the Air Force in New Mexico. And that sort of got her thinking that she needed to make her way into working in radio astronomy. And she also has a lot of arts hobbies, such as painting, fiber arts, jewelry, medieval recreation, and glamping. That sounds like a lot of fun.
It is.
So what was the actual transition or opportunity that got you from the Air Force to NRAO?
So I worked for several different companies and like cellular communications and microwave communications. And I was working for the railroad here in Charlottesville. I had moved back to my hometown to be near family because my grandmother had cancer. And while I was here, I went back to school, and I was going to school while working at the railroad. And I was taking classes, and Skip Thacker came and gave a talk during the classes one night, and I flipped out because I had no idea that this was here in Charlottesville. This is my hometown, and I never thought I would be able to like do my dream job here in my own hometown. So it was like kismet, and I pretty much accosted poor Skip afterwards, and I was like, you have to hire me. I don't think you understand. You need me. You do. And so he was like, well, you have to finish your degree first. So I did. I was like super determined then to just knock it out as soon as I could. And I did. And so I pretty much just started throwing my resume at the NRAO, and Skip came to talk again, and I was like, no, you have to hire me. You know, I need to work there. And thankfully the position came open, and I applied for it, and then I worked for Skip for the first few years before he retired. But it's great. It's what I've always wanted to do.
What is a typical day for you at
I spend most of my day in the room that you see behind me. This is a Band 6 receiver test set, and the receivers that Denise showed, it's my job to put those together, to test them, and to repair them when they come back if there's something wrong with them. For instance, just yesterday, I replaced an OMT, the ortho mode transducer we were just talking about. It's a very involved process. Just for the top section of that cartridge, there's 72 tiny, tiny, tiny screws. Ooh. And there are wires that are not much bigger than my hair. So yeah, it's a lot. It's very complicated. But I swear I never thought I would be able to do something this cool, but here I am, and I'm so excited every day. But I spend my day in the lab running tests, and there's another test set that you can't see in the picture. And if you hear any chirping right now, that's the cryo in that test set running right now to test mixers, because mixers are a part that go inside the cartridge that mix frequencies to bring them down to a level that we can mix with the incoming signals from space.
And the Band 6 receivers are all on ALMA, correct?
They are. And what's really cool about Band 6, and I didn't really realize this, I spent 14 years in a different department. I built the warm cartridge assemblies, which are the timing kind of source, the heartbeat of every band, every frequency band that we have. Mm-hmm. And so then I came across the street here, and it turns out that Band 6 is the band used for all the black hole science. So it's pretty exciting. All these things that come out every day from Band 6, and it's like, I want to say it's Band 6 and I helped.
You can say that.
Well, yeah, it is. It's so great every day. Every day there's something else that they've come up with. They've found using the ALMA Band 6. It's so great.
Can you explain a bit more of what Band 6 means? So here at the VLA, we talk about having receivers in S band and X band and P band. And those are different frequency or wavelength ranges to capture the light. So what is Band 6 capturing?
Band 6 is, I believe, 220 to 275 gigahertz.
Oh, so for reference, the VLA is 1 to 50 gigahertz. So this is much, much, much smaller, more energetic light when we're talking about radio and microwave signals.
We have cartridges in different bands that go even up to like 800 gigahertz. So we have some pretty high frequencies going on inside the doer on an actual antenna. It's amazing how close to a terahertz we really are inside ALMA.
You can pretty much say that you've touched every Band 6 that's in ALMA.
Not just every Band 6, because I worked for the warm cartridge assembly. Every single cartridge that's on every single antenna has a part that I built or tested.
So how many of those per antenna? 10, 8 or 10?
10. Mm-hmm.
And
Well,
66 antennas.
66, yeah. And then there are spares. So all total, it was like 780 that I built and tested across the street. And,
that's incredible.
It was amazing. It was amazing. I really was so in love with my job, and you know, being able to contribute and to do something that, you know, I can be proud of. And as a girl, oh my God. It's just been great. I'm really excited every day.
Now, with all of this hands-on work that has to be done, how has that been going during all of this pandemic stuff?
Well, actually, I think got classified as an essential worker. And I was out from March. I came back in May, and I was the only person here. And because we have antennas down at ALMA who need receivers. And when everything gets up and running, science is going to be ready. Once Chile has got everything running, I think they've just got it. They're bringing everything back into function now.
Yes, they are.
So we needed to be ready to support them and to have units ready to send them to keep the science going, because it's one thing in radio astronomy is you can't just turn it off and not do it, because everything out there is expanding and moving. So in order to get the science proper, you have to get it and do it at the time that you've planned to do it. So that's been pretty important. So I've been here all along.
We very much appreciate it, Jennifer.
Thanks.
So now I'd like to just bring on all three of you back. So Matt and Denisse can also join us. And our extra special guest, Bert, if you could join us. We also have Bert Hawkins, who is the Assistant Director of CDL. And just before we open it up to questions, Bert, I wanted to follow on from Jennifer mentioning all of the exciting black hole science. What is she referring to, and how was CDL playing a role in that? Oh, you're muted, Bert.
Thank you. Yeah, Jennifer mentioned Band 6 is a very productive band on ALMA, and it is the band that was used for the black hole. So imaging. So for years, we've partnered with the University of Virginia to build these very specialized superconducting devices called mixers, which allow us to see those frequencies. So not only did we work with UVA to build those devices and put on ALMA, but we were on 3 other telescopes on the Event Horizon Telescope. So, you know, many of the receivers on the black hole image you see had our equipment in it. CDL also had to make some changes to ALMA itself. We had to change the way the antennas take an image. You know, it's set up to be an interferometer now. We had to change antennas so that it acted as one single antenna, and we also had to upgrade some of the timing circuitry so that they all had the resolution to be able to do the imaging at those long baselines. So we were very much involved in the black hole imaging.
Very cool. People often, everyone coming out to the VLA, that's one of their first questions when they were still physically coming. And we were bummed not to be able to say the VLA, but we would always be pointing to ALMA. And I think those of us out here didn't fully understand that connection. So now we will both point to ALMA and also be like, have you heard of a thing called CDL?
Yeah, it was very exciting. We were very proud of the work.
Jennifer, I see that you marked a question that you would like to answer live.
I may not actually be the best person to answer that. It's about the low Earth orbiting satellites. I
can read it out.
Could the guests discuss the effect of low Earth orbiting satellites upon the research projects happening at VLA? Thank you, excellent presentation, appreciated. So I was thinking more like how Starlink and the things like that, the low satellites would affect ALMA, but
that works.
Let Bert answer that because he's probably got a whole lot more information on that than I do.
Right, it's a great question because it's a relatively hot topic now in radio astronomy. Between Starlink and the similar satellites that are planned in the tens of thousands, as you may know.
Yeah.
Car radars for autonomous vehicles are coming online. They're in our frequency bands. 5G, Internet of Things, all these things are going to be an issue in the future. And if you attended the NGVLA webinar, you know that is going to be distributed over a large part of the Southwest United States. So it's inevitable that we're going to have interference. So the NSF is leading an effort to really get a handle around that. And the first thing you have to do is measure your local environment around a telescope, how much interference is occurring. Once you have your hand on that, you can start exercising the interference and mitigating it. So Matt is actually involved in that. CDL is leading an effort to develop prototype software and hardware that would be sensitive enough and operate at high frequencies like ALMA and NGVLA will, to be able to detect that those interferes. And we're leveraging some of the NGVLA integrated receiver work Matt is doing. So that's a whole new mission for us at CDL. You know, we're used to building receivers for, you know, detecting these cosmic signals. Now we're detecting man-made signals.
Terrestrial ones.
It's a challenge, but it's a really great dual use for our technology.
Yeah, I always think it's ironic that one of the big interference sources out at the VLA is Sirius FM radio satellites.
Yes.
Because radio is interfering with radio.
Yes, that is a problem. In fact, I was in a meeting this week about that, and that's increasingly a problem. But the good news is there are a lot of things you can do to mitigate those effects. So right off the bat, they're not always there, right? These are low orbiting satellites who have to fly very fast to stay in orbit. So they're not in your field of view. Our field of view is very tiny. So it's not a disaster, but we need to get working on it because it is increasingly a problem.
And I believe NRAO or NSF, the National Science Foundation, and SpaceX are working together to get some sort of memorandum of understanding.
That's correct. To solve this, you're going to have to partner with industry, and that's part of NRAO's mission, is to do that engagement.
Yeah. Faith, I saw you flagged a question.
Yes. Also, I just wanted to say, Jennifer, someone in the comments mentioned that you have a fabulous dress.
Oh, thank you. I love space clothing.
So the question is, the components being developed at CDL are already small, but is there ongoing work looking into further miniaturization?
Absolutely. I'll take that one if nobody minds. So actually, can I share my screen here real quick?
Absolutely.
Yeah, so here's I was looking at this earlier. This is So for some of the stuff that Denisse was showing earlier, particularly like the cryogenic low noise amplifiers and stuff that are machined with such precision, very small, those are very much handcrafted parts actually to get the optimal best performance you can. But a lot of our electronics, you can accept a little bit of, doesn't have to be, not every part has to be an art project, in which case we use a lot of integrated circuits, little semiconductor chips like this one shown here to get a lot of miniaturization. I actually head what's called the Integrated Receiver Development Group, which is really focused on this. And let me skip past some slides here. I'll show you kind of how, again, we develop some of these custom chips for the higher frequencies. Some of them we buy off the shelf, others we develop. But these then go into integrated modules like this. And so that compacts a lot of electronics into a very tight area. And there's a lot of active research going on, particularly in the Integrated Receiver Development Group, to learn how to integrate these devices without giving up anything in terms of the sensitivity and the stability and the ultimate performance that we need for radio astronomy. We have to be very careful about it, right? Because we have sort of high standards of performance, and we have to make sure that we don't give up anything. We're also doing a lot of development in digital electronic technology, shown here, where a conventional solution for digitizers and that kind of electronics is shown here on the left, but we're doing some custom component design that's specially designed for the signals we detect for radio astronomy that allow us to put it in a much more compact form, as well as reduce the power consumption by a huge factor. So absolutely, this is a very active area of research.
That's amazing. We learned in our NGVLA event that partially because enough time has elapsed since we built the VLA and even since we updated it, that by the time we have NGVLA, even just the receivers can be so much smaller than the 2-story feed horn that we have for one of the bands. And it's incredible how much smaller everything can be. And so then the telescope design can completely evolve as a result. There is a question that's actually asking about BYU's low noise array. Does anyone know about that? I haven't heard of that. Just thought I would try you. But somebody is curious if they are exploring metamaterials as a potential tool for pushing the limits of phased array fed reflectors.
I believe the question is about
Very
phased
technical.
array. We did do some collaboration with BYU for the L-band phased array feed that's on the Green Bank telescope now.
Oh.
And yes, we have talked, I'm reading the question now, sorry, while I'm talking, but yeah,
okay.
coupling is one of those issues. So it's a question of the noise. Again, we talked earlier about electronic noise and how this sort of masks the signal we're trying to detect. And the issue is that when you have these phased array feeds, you're packing a lot of these antennas very close together so that they couple to each other, and you have your amplifier that's supposed to amplify the signal actually emits noise back out of its input, and then they couple over into the adjacent channel, and so they sort of cross-contaminate each other, and that's this mutual coupling problem. So it's really kind of a fundamental electromagnetic problem, and that's again another area of active research. I have not personally heard of anybody exploring metamaterials as a solution to that. I have seen metamaterial like band gap structures. Lisa Locke, who was on the video, had been doing some research in that as a way of making joints between components more sort of alignment tolerant and that kind of thing. But I haven't seen it as a solution for mutual coupling now.
For those of us that don't know metamaterials, can you explain what that means?
Yes, so when we design electronic components, we look at sort of the properties of materials, things like its dielectric constant or its conductivity and whatnot. And this all describes how that material behaves electromagnetically. A metamaterial is when you sort of control the geometry and the makeup of the material at a microscopic scale, or at least at a scale much smaller than the wavelength that you're trying to use it at. So that on a macro scale, it behaves like it has dielectric or conductivity properties other than what it naturally would have in the bulk form. Yeah.
Sounds like sorcery.
Yeah. Sometimes. Seems that way. Yeah, they even make materials that have like negative refractive index and stuff like that over a limited frequency range, which, like you say, is pretty magical. Nature doesn't do that. Yeah.
I do see a question that's in the chat about asking how elaborate does telescope grounding have to be? Does anyone feel like fielding that?
Grounding in terms of for lightning storms, or grounding from electrical viewpoint?
I'm assuming from an electrical viewpoint.
So yeah, ground continuity and ground quality, if you will, is a critical part of your electromagnetic circuit design. It's also a safety feature, again, because some of, for the high power systems that drive, for example, the correlator, you have to make sure it's grounded well. As far as it being elaborate, I mean, it's, again, for the high frequency stuff that we do, it all kind of scales with wavelength and all. And so it's all in sort of a microscopic scale when we do like these printed circuits, or as Jennifer talked about, the really tiny screws that kind of make sure everything is in good electrical contact and grounded at, enough points. But I hope that answers the question. I don't know.
We'll say that everything, because it's so small and because it's made the way it is, everything's much more susceptible to static. So we have to take a lot more precautions with ESD and wear wrist straps and ESD shoes, and make sure that we're very careful with all our workstations and everything else, so that we don't zap things before we ever get a chance to use them for what they're intended for.
Yeah, just over this winter, we had to install a new humidifier system in our building. Because when winter comes and it gets dry, the risk of static electricity damaging some equipment is increased. So that was a project we had to mix in with the COVID protocols we're following. So it's always something interesting going on.
Sounds like it.
Another question we had is, were your receivers optimized to measure the polarization of the black hole signals?
Yes, so the band 6, as mentioned for the OMTs, does do polarization separation. Matt, you may be able to elaborate on that.
Sorry, yeah, I was responding to another question. So, yes, indeed, the band 6 cartridges that were used do incorporate a very precise orthomode transducer. I think Denise showed a picture of one actually in her slides. This was used to detect the polarization. In fact, they recently published an update to that image, I believe, that showed the polarization signature of the material around the black hole.
That's what I was going to ask. I believe that picture had the polarization data in it.
I guess it took a little more processing.
Right, yeah.
It's an integral part of my testing also. We test for polarization accuracy and to make sure that there is very clear separation between them.
Jennifer, you mentioned the grounding and those other precautions, but do you have to work in a clean room?
It's not a clean room, but it is a closed HVAC area. It has its own HVAC system because.
What do you mean by it? Can you explain HVAC for?
Oh, sorry, heating and air conditioning system. Because during testing, it has to maintain 1 degree. It can't change more than 1 degree over an hour in order for the testing to be accurate, because that's up when it's installed on an antenna, the temperature does not change because of the environmental heating HVAC on the back of the antenna. That does not fluctuate. It's a set temperature and it stays at that temperature with that wind speed, that fans blowing in there and everything. So it has to mimic exactly in the lab what it does out in the field. So yeah, our heat can't go up and down all day. It's got to stay just the same level at all times. The same with the humidity, as we try to keep everything the same at all times. So my stuff's in a chamber, and so it has, you can't really see it there, but it looks like a huge meat locker.
Another thing about those chambers that might be worth mentioning is that they also have their own dedicated 50 hertz mainline power supply, I believe. As opposed to 60 hertz, which is what we use everywhere else in the lab. And the reason for that is it's, again, intended for use in Chile. And there was some concern that the efficiency of the cryogenic systems wouldn't be the same running on a 50 hertz power line.
Another question we have is, could you talk about some of the other work for others that you've been involved in? You mentioned the WMAP mission. Are there others?
There are others, and that's some work we're very proud of. So other observatories often come to us to leverage our expertise. I think Denise mentioned, we have a world famous low noise amplifier team. We've produced some of the best low noise amplifiers in radio astronomy for many a year. So, we've done work for our Japanese and East Asian counterparts on ALMA for low noise amplifiers. We also recently completed, Jennifer was mentioned, she used to work on the warm cartridge part of the ALMA. We recently did a very large project for a sister organization for that as well. That constitutes a significant part of our business. Related to that, I want to talk about some of the work that Matt does. The other mission we have, since we are funded federally, is if any of our technology can be used commercially and help the U.S. industrial base, we're encouraged to form those links and do it. And and Matt has invented this new technology called reflectionless filters, which is used by, I don't know, Matt, at least 20 companies around the world now. It's a licensed production, and it's finding its way in all sorts of technology, which just goes to show you that some of the things you built that to improve the receivers in radio astronomy, but it has applications in all sorts of other regions. And every day it seems like we're getting a new application for that. Matt and I have been dealing with a superconducting version of his reflectionless filter here lately. So yes, a lot of our work is for either sister organizations in radio astronomy, and increasingly it's for industrial partners.
To pick up that thread, because it also talks about one of the other questions somebody asked. So yeah, the reflectionless filters, that's been a very exciting thing for me to work on. It's kind of an interesting side task that I have these days, working with our commercial partner on that. I think it actually has hundreds of companies now, but that was an interesting thing. So somebody asked about some of the patents. Of the 17 patents I currently hold, that's probably accounts for maybe a dozen of them, because we developed it and then we improved upon it and we came up with new ideas and we improved upon it more. But that was an interesting technology. It had to do with the fact that a filter as an electronic component selects certain frequencies that you're going to pass and rejects others. And conventional filters do that by reflecting unwanted signals back out of their inputs, which causes interactions with adjacent components in your system and degrades the performance of your system in technical ways that I probably don't have time to go into. But we developed a kind of filter that absorbs unwanted signals rather than reflecting it in a very efficient way. And this is finding a lot of interesting use in academia. Some of the other things that we've patented have had to do with digital data transmission, also the orthomode transducers. That's an active area of research that we've done some things in as well, and also broadband feed horns or antennas. In radio astronomy, we're often, the astronomers want every frequency they can get from DC to daylight, right? And so we're trying to make our systems as broadband as possible. And so we've done some work on ultra wideband feed horns as well.
So we've just hit the hour mark, but I feel like everyone's having fun. And so I would like to maybe have one more question. Faith, if you see a good one.
Sure. Could you please talk about some of the new receiver technologies and new receiver bands? Are you working in multi-pixel receivers and terahertz receivers? So yeah, kind of a long question, but basically just asking about some new stuff related to the receivers and the bands.
I'll let Matt talk about his integrated receiver, but first, just it was mentioned earlier, one of the things we do is look into new technologies, and someone mentioned the traveling wave kinetic inductance pair amplifiers, which is not only a mouthful, but a promising technology. So that's another superconducting technology, which has the potential to even drive the noise lower on some of our ALMA receivers, because we're always bumping against theoretical limits, and we want to push past those. So that's a very early research project, and it does operate at just a few millikelvin above zero. We need to get it to work up to 5K, where ALMA does. But that has the potential to be a new detector and a new amplifier and improved performance on the ALMA receivers we built. And that's a good example of the longer term, more researchy type work we did. Matt has conceptualized an entire new way to do receivers that he's going to use on NGVLA he can talk about.
Yeah, so again, that's really focused. The question talked about multi-pixel receivers, and that's one of the big things that we're trying to do with that. If you kind of look historically at our receiver electronics, they kind of look like hot water heaters with huge bundles of components all plumbed together. And we're trying to get things more sort of semiconductor die and integrated. And the idea is that then it's something you can hold in the palm of your hand instead of the 2-foot high cartridge or even something bigger than that. And so you can pack arrays of them into the focal plane of your telescope and have multiple beams on the sky simultaneously. In terms of bands, we fairly routinely cover anything from tens to hundreds of megahertz to almost a terahertz with various telescopes and various sites. We have looked at some exotic new superconductor material stack-ups for doing things at I think at 1.2 terahertz was talked about at one point. You don't go much lower than 30 megahertz or so because of the ionosphere is starting to cut off there, and pretty much all of our telescopes, our main mission is ground-based telescopes. Though we do partner with NASA sometimes for spacecraft and high altitude balloons and things like that, where you can do lower frequencies and the ionosphere is not going to cut you off. So really between that range and like I say, up to a terahertz is sort of, there's really no missing bands other than where the atmosphere is just so opaque that that's not worth trying to observe from the ground. And then there are some work, we partner with groups looking at even higher frequency stuff, getting into the far infrared type electronics.
Yeah, let me follow up real quickly. We talk a lot about high frequencies. We have a team at CDL that specializes in low frequencies, below 100 megahertz. And what they're looking for is very early signals from the universe, the cosmic dawn, when the stars first started to form. And you can imagine that's very difficult. That's way back in time, so those signals have been stretched, so it's very low frequency, and there's a lot of universe between us and those signals. So, that's a whole different level of radio frequency engineering, and they're extremely talented, and they are working with NASA on some spaceborne solution to that problem, perhaps a lander on the moon or perhaps a small sat orbiting the moon. So we really do cover from very low frequencies to very high frequencies.
Amazing. I would like to thank you all for joining us today and also give you an opportunity to just sort of say any final words you want to about either your job or CDL or.
All right, I'll never let that opportunity go by.
That's what I thought.
We have an expanding mission at CDL. We talked about the spectrum problem. We haven't even talked about all the exciting radar things that are going on in NRAO now. And NGVLA is going to be a big project for us, and we're involved in upgrading ALMA now. ALMA is ready for ALMA 2030, the second generation of ALMA is coming. So at CDL, we're expanding, and we're particularly interested in students coming to work with us, particularly co-ops and postdocs. So if you or someone you know is interested in that, please get in touch with us. Visit our website. We're looking to expand both those programs, co-op students and postdocs. We will at a have 4 co-ops this summer, and we have 1 co-op now. We hope 1 postdoc, and we hope to bring that up to 4 in the future too. So we're an organization that's growing, and if you're interested, you've seen the magic now. Please check out our website.
Anyone else?
I'd like to chime in if
Yeah,
I could.
go for it.
I'd like to say that I've been here about 15 and a half years now, and I absolutely love my job. And imposter syndrome is a real thing, and we all battle that at some point. But work hard and do the things. You can make it, and you can do it, and you can be anything you want to. Live in proof. But I also want to point out how amazing the NRAO is in our commitment to diversity and inclusion, and the programs that we have that we're working on here to stay current with D&I and to move forward and progress and make real change. And I think that I'm really impressed with how we're doing, and I think that it's a really great thing. I I just wanted to say how proud I am of the work that the NRAO is doing and committing to. And that's, not a lot of places are committing to do the work, but we're really committed to do it. So I just wanted to shout out for that.
Thank you, Jennifer. I second everything you just said, and I appreciate it for bringing it up. Okay, so I'm going to throw it back to Faith, who is just going to wrap it up, tell you about what's coming next. And we have a brief survey that she's going to mention that we would love it if you could fill out before you leave today.
Thanks, Summer. All right, so our next tour is going to be 4 weeks from today, so May 22nd, and again at 1 p.m. Mountain Daylight Time. And so this is going to talk about the ins and outs of operating one of our radio telescopes, the Very Large Array here in New Mexico. And yes, thank you so much for coming today, and thank you to our guest speakers. And if you'd be willing to fill out the survey for us that we'll be sending out after this presentation, then it would, and provide feedback, then that would be really helpful for future tours. So thank you very much, everyone, and have a great rest of your day.